Hey everybody. Today we're learning how to generate random values from any distribution, not just standard ones like the normal or chi-squared distributions. Suppose, for instance, that we have the PDF f of x equals 2x, and we'd like to generate random values with that density function. The fundamental tool that we have at our disposal for doing that is this theorem. Suppose f of x is strictly increasing on the interval a comma b, where a could be negative infinity and b could be positive infinity, and that f of a is 0 and f of b is 1. And of course, if a and b are infinite, we need to have limits in there, but you know what I mean. The idea here is that big F is sort of the CDF of the distribution that we have in mind. Then if y is uniformly distributed on the interval 0, 1, then f inverse of y is going to have the CDF that we want. And then we can find the PDF just by differentiating. So let's actually generate 10,000 random values from the distribution that I mentioned a minute ago, the one with PDF f of x equals 2x on the interval 0, 1. The basic idea is we're going to compute the CDF, big F of x, take the inverse, generate random values from the uniform distribution on the interval 0, 1, and apply f inverse to them all. So basically just applying that theorem on that last slide using this PDF that we're given. When f of x is 2x on the interval 0, 1, the CDF, the definite integral of that, starting at 0, is x squared. You can confirm that big F prime is 2x here. We invert that. Since everything's positive, the inverse exists and is just the square root of x. Next, we generate random values from the uniform distribution on 0, 1 and apply f inverse to all of them. So in R, we can generate those random values with R unif, and then the argument inside of there is just the number of random values that we want. I called that y, and then I defined x to be the square root of y, so literally just taking the square root of each of those 10,000 values. The first line here, by the way, set.seed, is just resetting the pseudo-random number generator so that your results will be the same as my results if we run that same code. The first few values generated here for y are 0.337, 0.789, 0.781, and so on. Here's a histogram of those 10,000 results, and you can see very directly that this distribution has density y equals 2x, just like you would hope. The proof of the theorem that we're using is just an application of the CDF technique. It's short and I think instructive, so let's run through it really quickly. By the way, I have a whole video, the previous one in this course, on the cumulative distribution function technique. I'll throw a link to that up top if you're not familiar with it. So suppose big F has the properties of a CDF, like described in the theorem. Let y be uniformly randomly distributed on the interval 0, 1, and let x equal f inverse of y. The CDF of y is just the identity function, call it g of y, so g of y is y. And so then we can figure out the CDF of x. By definition, it's the probability that the random variable x is less than or equal to the specified value little x. X is equal to f inverse of y, so we just plug that in, and then we apply big F to both sides of that inequality. It's an increasing function, so it preserves the inequality. We get the probability that y is less than or equal to big F of x. This is a statement about the CDF of y, so we're going to replace the probability statement there just with big G. Big G is just the identity function, so g of f of x is just f of x. So what we've shown here is that the probability that big X is less than or equal to the specified value of little x is just big F of x. So that's what the CDF is. The CDF is exactly what we hoped it would be, big F of x. Let's do one more example. Let's generate 10,000 observations from the logistic distribution, which has this PDF. Little f of x is e to the negative x over 1 plus e to the negative x, quantity squared. The support of this random variable is all the real numbers. We're going to also want to generate a histogram of the results so that we can see the shape of this distribution more clearly. First, we need to compute the CDF of this random variable. So we're going to do that by taking a definite integral from negative infinity up to the value in question, little x. We're going to integrate the PDF, And I'm writing that using a dummy variable t so that I don't repeat my usage of the variable x. So integrating f of t dt. We carry out that integration by finding an antiderivative, plugging in the limits of integration, doing a limit for the lower limit of integration. Overall, we just get 1 over 1 plus e to the negative x. Now we need to invert this and apply it to some observations from the distribution u of 0, 1. You can verify directly that the inverse of 1 over 1 plus e to the negative x is the natural log of y over 1 minus y. Let's get some random values. Again, I'll set a random seed, set a seed in my random number generator here. I will get 10,000 values from that uniform distribution, call that y, and then define x to be the logarithm of y over 1 minus y. The first few values generated here are negative 2.05, 0.499, etc. Here's that histogram. You can see that the logistic distribution has generally kind of a bell shape. Its shape is similar to that of a normal distribution. Although you can see that it's not exactly a standard normal distribution. You can see that we have a substantial number of values larger than looking at this plot, larger than 5 and smaller than negative 5, which would not be the case in a standard normal distribution.